fascinating talk. As you know, the title is Arsenic, the Silent Killer, so I'm so pleased to see so many young people here because it's fun for all the family tonight. And we're very honored to have with us Andrea Foster, who is a geochemist. Andrea studied here at Stanford. She got her doctorate here, working actually with Gordon Brown, who I see at the back here, and is now working for the USGS in Menlo Park, down on Middlefield Road. That Andrea is also a user. She's a scientist who works at our synchrotron radiation facility here at SLAC. We're very pleased that she's accepted to talk to us tonight. So, Andrea Foster.
Thank you. Thank you for that. So tonight I'm going to be talking about arsenic. And we called this talk the silent killer because we're really going to talk about the modern day ways that arsenic is killing people around the world. But most of us probably know arsenic not as a silent killer, but from the old days when it was used as a poison. And I'll talk a little bit about that. I'll give you a little bit about the history of arsenic and how it was used in the past. And then we'll go into the modern day issue and talk a little bit about the many factors around that problem. And the focus of the work that I've done here at SSRL and at other synchrotrons is really applying the X-ray techniques that we use here to study arsenic in its many forms. So the big problem with arsenic is that in Bangladesh, millions are being poisoned right as we speak by arsenic in their drinking water, and the consequences can be fatal. There are an estimated 21 million people that are currently being exposed to levels of arsenic considered harmful, and about 3 million people are exhibiting symptoms of arsenic poisoning. In neighboring West Bengal, India, which is just on the eastern side, shares a border there with Bangladesh, there's an estimated 1.5 million people exposed and some 200,000 showing symptoms. The people that currently of the people that have symptoms, it's estimated that as between 200,000 and 2 million people in Bangladesh alone will die of cancers that are directly related to arsenic poisoning. For comparison to some more modern industrial poisonings, Chernobyl, where there was a release of radioactive material, only killed directly 56 people, although a lot of people got thyroid cancer, but that is treatable. Bhopal, India, where a toxic cloud of cyanide vapor spread over the city, killed 4,000 people in one terrible evening. But those numbers really pale to what's going on in Bangladesh. And the worst part of the whole story is that it could have been avoided. Prior to the problem that the Bangladeshis are currently experiencing with arsenic, they had problems with really high rates of infant mortality, and there was a famine in the 1970s, which is being shown in this Time magazine picture. The problem really started as early as the partition of India in 1948, in which India was split up into two countries, India proper and Pakistan. There was a West Pakistan on one side of India and East Pakistan, which is modern-day Bangladesh, on the other side. West Pakistan, as the story goes, got the lion's share of the budget for the country. So Bangladesh really didn't develop a lot of infrastructure. I mean roads, I mean electricity, I mean sewage treatment plants and piped water, the way we do have here. And so a lot of people live still in agriculture. The majority of the country still works in agriculture, and the country suffered from that. In 1971, there was a war for independence from West Pakistan, and that war was pretty horrific. Some have used the word genocide to describe what happened in Bangladesh, and that further hurt Bangladesh and exacerbated the famine that was going on. But having developed for a long time was this issue of contamination of the sources of drinking water that up to that point had been used. And those were mainly the rivers and the ponds of Bangladesh. And so what you had were a lot of diarrheal diseases, typhoid, hepatitis, and a set of related conditions related to microbial contamination of drinking water. And that's what was leading to the high infant mortality rates. Bangladesh is a country that is severely overpopulated, according to the CIA fact book. It's about the size of Iowa, with about 48 times the people, about 125 million people. So there's a lot of people to feed. And there's also yearly some really, really heavy rains called monsoons that basically flood about a third of the country. Most of the country is right 10 meters above sea level, so if there's any heavy rains, just everything gets flooded. It's very flat. And a lot of the country during the monsoons is navigable only by boat. And of course, you can't grow food on that land that's flooded at that time. Famine was so bad in the early 70s that one of the first aid concerts ever given, or I think it was the first, was put on by George Harrison, the former Beatle. He learned about the situation from Ravi Shankar, who I believe is an ethnic Bengali, and the Indians of West Bengal and the people in Bangladesh share the same ethnic background. So that was the first aid concert, and a great success, but as you see, focused on the famine issue. But the issue of the contamination of the water was a big one. And so a lot of non-governmental organizations, such as UNICEF, led an effort to find a new source of water for the people to drink. Well, it so happens that Bangladesh is rich in water underneath the ground, so-called groundwater. And you can get at that groundwater very easily in Bangladesh. It just takes a group of fellas with a little pipe and a concrete sort of hammer to drill a well, even down as far as 150 meters. There's no bedrock to speak of in Bangladesh, so you don't need an expensive drilling rig or anything that we would need in this country. And that's because there's just a huge, thick package of sediments. We'll talk about that more later. So from our perspective, it was pretty cheap to get a well put in, but there was still sort of a status symbol in that country. But everyone who could get one, because there's not a lot of piped water outside of the main city of Dhaka, everyone that could get one would have one for their household water supply. And now there's an estimated 10 million of these hand-drilled wells. The problem is that before this countrywide effort to switch water sources, no one ever tested for arsenic. And that was an issue, even a litigious issue. There were lawsuits brought about that because some people think now that the scientists who were behind the decision to switch to groundwater should have known better. It's a little touchy, and so far the lawsuits haven't been successful. But at that time, the early 70s, we were just beginning to understand that arsenic could be quite pervasive in groundwaters, and we were just developing the techniques that would allow for measuring low levels of arsenic. So it's a hard issue to say who was right or who was wrong, but the point is now there's these wells. And across most of Bangladesh, arsenic levels in groundwater exceed the levels that we would call safe. This is a map of Bangladesh, which is a sort of smooth image of a sampling of 4,000 wells across the country. And we're looking at arsenic concentrations in the groundwater, where the dark blue are the lowest concentrations, and the red to that brownish color there in the middle are the highest. Now, the lowest concentrations would be on the order of 1 part per billion. For any chemists in the room, that's microgram of arsenic per liter of water. The highest concentrations on the order of greater than 300 parts per billion. Now, what are safe guidelines? In Bangladesh, the guideline is 50 parts per billion. Water having arsenic concentrations greater than that is considered to be unsafe to drink. Water below that is okay to drink. Of course, that is just a number, sort of you got to put a line somewhere. But I wouldn't want to be drinking 49 part per billion water. The World Health Organization, that's WHO, and our own country have a guideline of 10 parts per billion. The United States actually considered having 5 parts per billion and 3 parts per billion as safe levels, but it was decided that it would be too expensive for all of our water companies, the people that provide our water, to meet those criteria. So actually in our country, we accept a greater level of cancer risk from arsenic in our water than we accept for a lot of other toxins in our water. The silent killer, arsenic, in drinking water takes decades to work, and I hope everyone has eaten. Some of these pictures can be a little gruesome. It took time to discover the problem in Bangladesh and West Bengal, because it takes about a year for people to start or 10 years rather, for arsenic symptoms to start to show up. And one of them is shown here. It's called keratosis, and it's the hardening of the soles of the palms, or the palms or the soles of the feet. And often they get so hard and crack, and you get infections in the cracks, and it can lead to gangrene, and it's very painful and debilitating, though not fatal. There's also hyperpigmentation or freckling. I have plenty of freckles. I wonder if all my years of work in arsenic has something to do with it. And there's also hypopigmentation, which is white spots. But all of these symptoms together are called arsenicosis, or arsenic poisoning, though there's no clinical definition of that term. And after about 20 years, you start to see skin cancers develop. And the type and location of these skin cancers are really special for arsenic poisoning, as opposed to the kind of skin cancer you'd get from too much exposure to the sun, for example. And a host of other effects are observed. After about 30 years, the fatal cancers come on, the internal cancers, particularly the bladder, the kidney, and the lung. And there is some evidence to suggest that there's a synergistic effect between smoking and drinking arsenic-contaminated water on the lung cancer. There's also a special kind of diabetes that is related to arsenic poisoning, and a host of other illnesses. Cancer risk is directly related to the amount of arsenic that you drink. So if we have 1,000 people drinking 1 liter of water a day, the risk from developing skin cancer, if you're drinking water at the Bangladesh standard, 50 parts per billion, is 1 to 2 people out of that 1,000 will develop a skin cancer. If you drink 10 times that much, if you drink 500 parts per billion, then 100 people out of that 1,000 will develop skin cancer. And the deaths from internal cancers scale accordingly. So it's really better, the less arsenic you drink, the better. But as I said, we all know arsenic as a violent and rapid killer. And one of the best descriptions of arsenic in its historical use as a poison was given in Madame Bovary, which I had to read as a high school student. And that includes vomiting and convulsions and diarrhea, a process I think that took Emma Bovary several hours. But it occurs really rapidly. And one particularly gruesome consequence is that once dead, the corpse develops sort of a blackened skin, probably due to bursting of the blood vessels right at the surface of the skin and blood collecting on the skin. This actually comes to play in a couple of other famous arsenic poisoning cases. One was when Nero used it on the advice of his court poisoner to kill Britannicus, who was the true heir to the throne by birth, but Nero became emperor at 14 or so, and used it. There was Nero, in those days, they had tasters. Poisoning was so rampant that they had people come taste your food, and then it would be safe to, if they didn't fall down dead, then you could eat it. So the way that Nero pulled this off is that he put the arsenic in a glass of water, and gave Britannicus rather, was having his first course, which was some broth, a soup. And the taster tasted it, it was fine, but it was too hot. It was purposely served very hot so that Britannicus would want to cool it down, which he did with his handy glass of water. And that's the story from there. But Britannicus developed those symptoms of blackened skin and so on, and Nero wanted to hide it. So he had them put makeup on Britannicus's corpse, and as they carried Britannicus to the place of internment, the mausoleum or what have you, it was raining and the makeup got washed off, and so everyone saw that Britannicus was poisoned. A similar issue came up in the case of the Borgias. The senior Borgia was also a pope, And he and his son went around poisoning everyone that they didn't like. And they poisoned for power, and they poisoned for money. And they poisoned to marry off Cesare's sister, Lucretia. And the story there goes that their favorite method of poisoning was to put the arsenic in wine and have a nice dinner and off their cardinals that way. So one night when they had planned to kill someone else, Cesare arrived earlier with the deadly bottles of wine. And he told the servant, hey, these are special bottles. Keep these to the side and don't open them until I tell you to. Well, the Pope arrived a little bit later. And he's really parched from the long journey. And he said, please bring me a glass of wine. That's all they drank back then. And so the servant thought, well, hey, it's the Pope. He's got to have the best. So he opened one of the best bottles of wine and served him the toxic stuff. And he died. And it was typical back then for the Pope to be laid in state, so people could walk by and see, just like what happened recently when the other recent Pope, Pope John Paul, died. But the deal was that with this blackened skin and the tongue protruding, he really made a gruesome sight, and they didn't keep him on display too long. So arsenic was such a popular poison because its most poisonous forms are inorganic. That means there's no carbon atoms involved, no complicated organic chemistry going on, and also that it's easily produced from natural minerals. So these are a couple of natural minerals. One is orpiment, is nice golden arsenic sulfide, and the other one is this silvery arsenopyrite. It's another sulfide that contains iron as well. And if you just roast this stuff, as they might have done in the Middle Ages, as shown here, then you get this white powder, arsenic oxide, and a fatal dose of this stuff is about 5 milligrams, 0.005 grams, very small amount. I think I estimated that the amount in this dish could kill about 1,000 of us. It's still used in rat poisons and ant poisons to this day. So in your hardware store, there's some toxic stuff. And it's also a starting material for a lot of industrial uses. But it's these same inorganic forms of arsenic that are the most toxic in our drinking water as well. And that's different than some other toxic metals such as mercury that you might have heard of, where it's an organic form that's very important. And there are two basic inorganic forms of arsenic. One is an arsenic 5, has a 5+ valence state. We call it arsenate. It's always surrounded by 4 oxygen atoms like this. We find it mostly in water that has oxygen in it. That would be water in rivers and water sort of at the surface of ponds. It likes to stick strongly to mineral surfaces, and that has big implications for how it moves through water systems underneath the ground, where it's in contact with minerals all the time. Its carcinogenic effect comes from the fact that it substitutes for phosphate, which is present in a lot of our body systems, but especially in our DNA, and thereby causing genetic damage. So arsenic 3 only has, it's called trivalent arsenic or arsenite. It only has 3 oxygen neighbors, and it keeps those always. It's predominant in oxygen-free water or low oxygen water, such as you might find at the bottom of a pond in the middle of the summertime when all the oxygen's been depleted from the water, or underneath the ground. So that's the kind that we find mostly in groundwater. It sticks weakly or less strong than arsenic 5 to mineral surfaces. So that's usually the one we find in water. And its carcinogenic effect is that it binds to sulfur in our proteins and in our enzymes. But both forms are highly toxic, and if you have either one around, it's not good. So around the world, it's this movement of arsenic between sediments and water that really causes harm. And that there's sort of displayed on this map are different areas of the world where arsenic in water is a concern. And I really want to highlight those tan zones. Those are where arsenic is in the groundwater, causing problems. The red dots are where arsenic is in water, either at the surface or the ground, underneath the ground, related to mining operations, and it's found a lot from mining operations. And then the green dots are where arsenic is coming into waters based on geothermal activity. That would be warm or hot waters coming up from the ground, carrying arsenic in solution, getting into the water. Now, an aquifer is a particular zone of rock or sediment in the ground that is holding water. And when we drill wells into the ground to drink water, we are tapping into one of these aquifers, such as in this cartoon. But an aquifer always has a layer above and below, more or less, called an aquitard or aquiclude. And this is a stratum that does not hold water. So it sort of acts as a barrier for the water to move up or down, except for where it's piped out specifically. Just some geology terminology that we'll need to know. And I wanted to point out that Asia is particularly affected. And this is the zone that we'll be talking about most, is Southeast Asia. Now, you might have noticed, I meant to point out, that some of these zones are very large relative to others. Especially there was a zone in the western United States that looked quite big. But it really has more to do with how many people are drinking that water rather than if there's arsenic in that water. And in the western US, currently, we're not really drinking much of our groundwater, though that could change as our population grows and we put more demands on our diminishing water resources. So a little arsenic in aquifer sediment can create a big problem in the groundwater. And I've shown you that in this cartoon. Let's say we have a little cube, a kilogram of aquifer, and it has 30% water in it. The amount of arsenic in the sediment is 3 milligrams per kilogram of this aquifer. 3 milligrams per kilogram is a typical background concentration for arsenic in any sediment. If you walk out in your yard in your house and pick up some sediment and analyze it for arsenic, you might come up with 3 milligrams per kilogram. It's not unusual. Let's say that there was just 1% of that arsenic released into the water that's being held in this sediment. That water's here and it's about weighs that much. You end up with 100 parts per billion arsenic in the water. If you remember those standards I showed you earlier, it's quite well above the standards safe levels. So you don't need a lot of arsenic to be released from the sediment to cause a problem. But the question is, why is the arsenic released? Where is it released? When is it released? And how fast? Those are really the key parameters that determine whether there's going to be a problem with the natural arsenic that's present or not. Because, of course, there's not a problem everywhere. So let's turn back now to Bangladesh and talk about our specific work there. Our work started because President Clinton came to visit Bangladesh in 1999 on what was billed as a goodwill trip. He was going to visit a village and watch some cultural displays, but he ended up not even stepping outside of the embassy because he was scared of terrorists. And guess which terrorist he was particularly scared of? Osama bin Laden. So he didn't see Osama, but a lot of Bangladeshis were upset because they thought Clinton might have had an ulterior motive in coming, which was in negotiating some of the licenses for lucrative oil and gas deposits in Bangladesh. And the United States was heavily involved at that time in the exploration in that country. But Clinton learned about the arsenic problem, and he asked his team of geologists, that's us at the US Geological Survey, to investigate what we could. And this was the team. We had a lot of help from the Geological Survey of Bangladesh and the Bangladesh University of Engineering Technology. But there were lots of geologists from within the USGS that specialize in different types of science that were working. This just shows one of us, Jim Yount, out in the field. He's collecting sediments from this pond in the back. Pretty low-tech operation, that one. But I didn't actually get to go to Bangladesh. I was busy having a child and other things. But I heard they had a lot of fun there in the field and always had an audience and a lot of help when they went out to the field. So our work, we really wanted to describe the geochemical factors behind the problem, the what, the how, the where, and all those things I mentioned. We want to identify what was the source of arsenic. We know it's natural, but what was it? We want to talk about and test some of the theories that were already being spread around about how arsenic was distributed and investigate the potential for future release of arsenic from some other sources of groundwater that the Bangladesh government is trying to decide whether they should start to use or not. Those items in blue are the items that particularly we used X-rays, this type of synchrotron sources that we have here, to address. So it's really important that we identify the arsenic-bearing phases in the sediment. And I use the word phases because we're not always talking about a mineral. A mineral is a material with a three-dimensional periodic repeating structure and a defined chemistry. But in the natural world, things don't follow those rules in your chemistry books. So a lot of times we have materials that don't have a set chemistry or don't have a set order, and we can see that with the kind of X-rays that we use here. It's critical to identify these phases because the dissolution, destruction of these phases is going to control how much arsenic is released. So we talked, one of the important phase is pyrite, iron sulfide, also called fool's gold, and now you have yet another reason to name it fool's gold. In the presence of oxygen, it dissolves very fast. It's destroyed really quickly. But in the absence of oxygen, very slow. So underneath the ground, in groundwater without oxygen around, it's going to stick around and be just fine and hold on to arsenic. But at the surface of the ground, it's going to release arsenic. When it is destroyed, it turns into what we call iron oxyhydroxide, but you can just call it rust, the same kind of rust on your bicycle chain. This material, in the presence of oxygen, will stay around for millennia. It doesn't go anywhere. And it really likes to hold on to arsenic. But if there's no oxygen around, iron oxyhydroxide is destroyed very rapidly and can release its arsenic to water. There are other phases that have sort of intermediate activity with respect to dissolution, such as siderite, an iron carbonate mineral that can also hold arsenic. It's also important that we identify the valence state. We distinguish between these two forms, not in the water now, but in the sediment. And the reason is that, as I mentioned, pentavalent arsenic sticks to mineral surfaces. It won't go into the water, whereas arsenic-3 doesn't stick as strongly, so it's much more likely to go into the water. But the problem is, how do we identify the valence of arsenic that's hidden in soils? That's one of the great difficulties because our standard geochemical toolkit really can't find arsenic, especially when it's hidden in other phases at low concentrations. So here we're looking at about 1/2 meter of aquifer sediment from Bangladesh, and you see there are some zones and stripes, some dark zones and some shiny minerals, and there's like 1,000 or more, 1 million different grains in there. You know, how do we start trying to see which grain is holding the arsenic? Well, we use our standard techniques are bulk. We take a bunch of that soil and we might dissolve it in really strong acid and measure how much arsenic is present in all of the grains put together. We might use X-ray diffraction to see what the different minerals are. Now, with that technique, we can only look at the well-defined minerals, not these other amorphous phases that I mentioned. We might also use different set of reagents to dissolve just parts of the sediment. That's sequential dissolution. And from that, we can learn things about, we get a hint about what kind of phases the arsenic might be associated with, but we don't have a definitive ID. And also, we get an idea of the strength of the arsenic retention on the solids. How easy is it to pull it out from the sediments and put it into the water? But that's not getting right at what we want to know. We also have some microbeam techniques that we can use in the laboratory. They might let us identify which grains have arsenic in them. And we might, from the chemistry, that we can put a small beam on one grain and get some chemical information, we might be able to infer what kind of mineralogy it is. But we really can't answer these questions about the arsenic valence, exactly identify that phase, map the distribution of arsenic on different minerals or phases. And there's something about the physical association of arsenic that can tell you something about whether it came and stuck on that mineral later or earlier in the process. And also, we need to sample a lot of grains, not just use a microbeam technique. And so for these things, we've used the synchrotron, like here at SSRL. Here's an overview, aerial view of the synchrotron here at SSRL. There's a place where we generate the photoelectrons, and they're injected into this big ring. And we have experimental stations that sort of come off at tangents, and the intensity of the X-rays that we use in this facility are much, much greater than anything you could find at your doctor's office or even in a laboratory source. And that lets us look at arsenic when it's in really low concentration in sediments like it is in Bangladesh. At SSRL, we use a relatively large X-ray beam. This is a ruler for scale, so it's really not that big. This is a sample from Bangladesh, and I've loaded it into this little Teflon holder and put a special piece of tape around it. And the beam that we use pretty much goes all the way across that sample, and so we get to look at hundreds, if not thousands, of grains all at once. And we get a sense of which forms of arsenic are predominant in the system, which is important to know. At the advanced light source up in Berkeley, there's another synchrotron. And that one, we use a microbeam on the order of 5 by 5 microns. Pretty small. And this is a sample getting loaded with a little tweezer. So you can see how tiny it is. And with that, we get information on a grain-by-grain basis, and we can map chemistry and also detect some minor forms of arsenic that we might miss with the bulk technique and understand something about the spatial relationships. So with both techniques, though, we get a certain kind of information called X-ray absorption near-edge structure spectroscopy, and it's sensitive to these issues of arsenic valence. And the way that it is sensitive to it is that energy of these spectra. This is one spectrum of arsenopyrite that you saw earlier. I don't know if you remember. In arsenopyrite, arsenic has a nominal valence of -1. And the energy position of the peak in the spectrum is going to increase with increasing oxidation state. And I'm going to show you an example of that. So here we have orpiment, where we have arsenic 3+ bound to sulfur. Here we have arsenic in water. It's hard to see there. Maybe we should turn the lights off. But it has arsenic 3+, when it's bound to oxygen, has a little different electronic structure than when it's bound to sulfur. And that makes a shift, even though they're both nominally 3+. And then here we have arsenic 5 on rust, on that iron oxyhydroxide that I mentioned. You might also notice that there's sort of a unique spectral shape. Each has a sort of spectral unique shape, and we use those like fingerprints, really, chemical fingerprints, to identify what kind of species or what kind of phase arsenic is associated with. And we do that by fitting. This orange spectrum is a natural sample from Bangladesh at 10 meters down. And we fit it with some model compounds. And we can see how much arsenic 5 is there, about 14%, and how much arsenic 3 is there, about 87%. So I'm going to give you an overview of our results and then sort of take you through those results. So what we've found is that there's a cycle here of creation and destruction of iron minerals. A lot of those ones I just showed you pictures of, in fact, and that leads to most of the arsenic being trapped in those minerals. And it all really has to do with whether oxygen is present or absent, or that's a very big control. So if we start off with pyrite, in the presence of oxygen, I told you that it goes very quickly to this rust material. But if this pyrite has 1% arsenic, this rust can easily accommodate that same 1% arsenic. Little arsenic is going to be lost during that conversion. But if we bury, and arsenic 5 is the main form of arsenic that we're going to have on that rust. If we bury that rusty material underground and let water pass over it and get it in a situation where there's no oxygen, we can start to form other phases. First of all, if there's sulfide present, we can form pyrite again. But it doesn't have that same morphology, of course. I'm just showing you the same picture that you saw. If we have phosphate present, we can form another phase, an iron phosphate, that beautiful blue material called vivianite. It can also hold arsenic. If we have carbonate present, which is usually the case in the ground, we can form siderite, that iron carbonate that you saw earlier. All of these phases can accommodate arsenic, and we have seen evidence for all of those in the sediments of Bangladesh. Under the ground, as I mentioned, arsenic 3 is the main form of arsenic, and when it's entrapped inside these sediments, we also see mostly arsenic 3. But it's going to be the dissolution characteristics of these materials that control the release of arsenic in that case. But we think that arsenic bound on the surface, not inside the structure of these minerals and other types of solids, might be key to the arsenic in the groundwater. And that's mainly because even if most of the arsenic is trapped in those minerals and just a little bits on the surface that can come and go easily from the surface, as I showed you earlier, it doesn't really take a lot of arsenic to be released to make a big problem in the water. So there's two ways that we could have arsenic stick on the surface, and I've sort of shown a cartoon of them. One would be a direct absorption where arsenic, like arsenate here, goes down and sticks to the surface of a mineral. I've shown the top of the mineral is here in these black oxygen circles. These green balls might be iron down in the rust material, for example. And arsenics come down from the water and stuck right on there and form chemical bonds with this oxygen. In contrast would be something like sulfur. When it's in its most oxidized form as sulfate, it does not really like to stick to a mineral surface. It just sort of floats above. it's electrostatically attracted to the surface because it, with all of its oxygen atoms, has a negative charge, and there are positive charges that it sees near the surface. So it comes down, but it comes close, but it doesn't stick. So this indirect absorption species are very easily released to the water, whereas directly absorbed species are less easily released, but they're still easier to get out than when arsenic is trapped inside of a mineral, like I showed you on the previous slide. And it's the water composition, such as acidity, that's what we call pH, how much acid or lack of acids in the water, the amount of sulfate, carbonate, phosphate. They also compete for sites on the surface. They might knock arsenic off. In particular, phosphate can knock off arsenic. That really control the release there. So, to Bangladesh and to what we've seen. Well, pyrite begins the story way up in the Himalayas, which are ultimately the source of arsenic to the sediments. And it also ends the story down in the south, where sulfur coming from seawater at depth makes new pyrite. And I'm showing you an electron micrograph of a real pyrite grain that we've seen there. But the question is, what happens in between? That's where most of those 10 million wells are. So that's really the critical place to understand the groundwater concentrations. But in the north, I'm showing you here a picture of Bangladesh. It's sort of a funny view. North is here on the left, and south is here on the right. Here's the Bay of Bengal, and this is the country of Bangladesh, like that. You might notice that two of the big rivers that feed Bangladesh, the Ganges and the Brahmaputra, or Jamuna is called inside of Bangladesh, really start in really different areas of the world. They sort of go off. So it's kind of hard to imagine that the source of arsenic could be anything but natural. If you remember the map of the groundwater arsenic concentrations, it was basically the whole bottom third of the country that has the problem with arsenic in groundwater. Although some people have suggested that there might have been industrial sources of contamination that created the problem, or even that laying phosphate fertilizers on the ground, which contain a small amount of arsenic, could have created the problem. It's really not likely when you consider the sources of the very disparate sources of the sediments that are coming in. But we went up here to Nepal, which sort of feeds the Ganges, and we looked in this area called Parasi, where they have their own little arsenic problem going. And we found that we could see pyrite, arsenic and pyrite, way up there. And so here's just another view of Parasi to the north here and the south here. These rocks, called the sawalics, contain pyrites, and we were able to see them very clearly in the electron microscope. And there's so much arsenic in them that we could even measure it with the electron microscope. We didn't have to come to the synchrotron and do it. So that was pretty clear. And it's some other things that we did, looking at the sediment coming out of this river, the Narayani, support the idea that arsenic is hitching a ride down to Bangladesh on rust. And so I'm showing you here a XANES spectrum of the kind that you just saw. And remember that the energy of the peaks in the XANES spectrum correspond to oxidation state. So this small peak at lower energy is arsenic and pyrite, and this big peak is arsenic in its 5+ oxidation state. And you can see from the size of the peaks that there's a lot more arsenic 5 than there is pyrite. And so that suggests that a lot of the pyrites, even so close to the source, are being oxidized and turned into rust, and the arsenic is traveling in that form. We also can see that. We looked at mica grains from the sediment, and micas tend to look, when they're edge-on, they look like these sort of sheets or books. And all this kind of grungy material there is rust. We can tell that. And so we have the kind of absorption, direct absorption that I mentioned to you in the previous slide. Here's another picture of micas. It's, again, kind of hard to see from the lights maybe. But when micas have iron in them, like this biotite, they're dark brown. And when they don't, like this muscovite, they're sort of pale or colorless. And we found that dissolution of these iron-rich micas, like the biotite, drives the formation of some of those new iron minerals, and that they hold arsenic. So when we went up to the ALS, we were able to make maps such as this one. And this is a chemical map of a whole bunch of different mica grains, micas only, because we found that micas contain more arsenic than other sediments. And you can see the blue is the fluorescent characteristic lines of fluorescence from iron. So all the blue or purple is iron, and the pink color is arsenic. So what jumps out at you are that some grains, some micas contain arsenic and some don't. And also that This is the only mica that's laying down flat like these. And you can see that the arsenic is right around the rim of it. All these others that look sort of acicular or lathe-like, they're standing up on edge, like those book sheets that we saw. So if we look at which micas these are, we find that only micas such as this biotite that have been heavily weathered, that have been attacked by water and time, actually have the arsenic with them. So it says that the arsenic is secondary, that it came later on and attached itself to these micas. We can look at those more closely with the electron microprobe and see those phases. Here we don't really have the same kind of resolution spatially or ability to image that we do with the electron microprobe, but we can image the arsenic, which we can't do over here. So it's very powerful to have the two together and see that phases like this correspond to bright spots like that on the same grains. Now those phases we've identified to be the vivianite, the iron phosphate that I mentioned, and the siderite, and we find both arsenic 3 and 5 in these new phases. These minerals prior to our work had not been thought to be important to the whole arsenic story. It was really all about rust. It wasn't about arsenic in these other kinds of minerals. And it certainly wasn't about arsenic in mica. So we find arsenic in pyrite and in mica, and it travels down to Bangladesh, where it gets buried and becomes part of the aquifer sediment that is feeding these wells. We have some that are down about 70 meters depth, and some that are even shallower. And down here, there's a hypothesis that the dissolution of this rust material really is the driver for the arsenic release. Now, I've already shown you that we see, in addition to rust, we see these other phases. But we found something else that was really interesting, which was that up near the ground surface, we can see arsenic changing from rust to other forms, right near the ground surface. And it also correlates with a change in color. So this is a pit that was being dug to make a pond to grow shrimp in. Aquaculture is called. And you can see this really dramatic change of color right here. We took samples out of that pit, and with XANES spectra, we were able to show that arsenic is in the 5+ valence state until it hits this blue-gray stuff, and then it becomes arsenic 3. So arsenic 5 decreases. This graph is showing the percent of arsenic 5 with depth in that pit. You might also have noticed that there was a band, a sort of orange band. Here's another picture of the orange bands. These orange bands contain a lot of arsenic, way more than the background concentrations above and below, about 4 parts per million. Within that band, about 250 parts per million. These kind of concentrations were not considered to be present, were not known before our work, and have some pretty dire implications. We puzzled a while about how these things form, and we think that they form due to capillary action. Now that's the phenomenon that if you have, let's say you had a glass and you have several tubes, straws of different diameter, tiny little straw and a big fat straw, and you put them into the water to the same depth, you'd find that that water would rise up the tiny little straw higher than it would the big diameter. This is because of cohesive and adhesive forces. And the same thing is going on to form these bands. So below this water table, the pores in the sediment are full of water. Above the capillary fringe zone, they're full of air. In between, there are different sized pores, micropores, mesopores, just like these straw analogy that I mentioned. So water can move up the tiniest pores into a zone where it encounters oxygen. Now that water that's moving up contains a lot of dissolved arsenic and dissolved iron and manganese. And as soon as it hits that zone of high oxygen, a lot of chemical reactions take place, and you form a rusty band, and arsenic gets sucked up on it. And over time, this can happen over and over and over again and accumulate arsenic. So we think this is an ancient process. But it has dire implications for modern agricultural uses. We've seen the bands at many locations now, although they don't occur everywhere. But here's a very dramatic example of a band formed underneath a field where they're growing vegetables. And back here in the corner, there's a little pump house. That's water coming out, if you can see that. So just think about saturating that band with water over and over for several months of the year. You could potentially dissolve that band and release arsenic to the groundwater. And remember, it doesn't take a lot. So if you have a really concentrated band of arsenic, you can really concentrate it in the water. Also, I mentioned the whole aquaculture thing, and this is the overview of that same pit that I showed you earlier. So if they fill this up and start growing or raising shrimp in there, you could get dissolution of the band and arsenic uptake in the shrimp, which would not be good. Although, luckily, the form of arsenic in shrimp is supposed to be one that is not very toxic. It's been shown that it passes right through our bodies. It's an arsenic sugar. But still, I wouldn't want to be the guinea pig for that. But we do find some places where deep under the ground, arsenic in rust has still survived to this day. So I just showed you a situation where arsenic in rust is going away really rapidly. But sometimes it persists. And it formed way back in a period when there were a lot more glaciers than there are now, and the sea level was low, and parts of the earth that are underwater now were exposed and got oxidized, and a lot of rust formed. And then the glaciers melted and was quickly buried. And so we still see that material, and our spectroscopy shows that it has a great potential to release the arsenic. I'm showing you a cartoon of one of these profiled through one of the wells that we dug. And we encounter this rusty material about 24 meters. Then next to that, I'm showing the total arsenic in the sediment, the total arsenic. And the green line is sort of the background arsenic concentration, what you'd expect anywhere you go. So we actually have an enrichment just at the transition sort of between gray and brown in this sediment. And by X-ray absorption spectroscopy, I've shown that in the gray material below the ground, we have a lot of arsenic-5, and in the rusty material, we have a lot of arsenic-3. So again, there's still a potential to release arsenic in this stuff. Some, working in other locations than we are, have advocated using color as an indicator of where you can site a well. So where these other scientists are working, the brown sediments actually don't, if you put a well into the brown sediments, the water that you get out is low in arsenic. So they have suggested that people use that as an indicator. But I wouldn't agree with that, at least in this site. There's sort of a peak in total arsenic and a peak in the dissolved arsenic. So the X-rays, I've given you some examples, not all of our work, but sort of to explain how, why, and where of all this issue. The arsenic came from the Himalayas. There's no smoking gun source. It's everywhere. And how is arsenic released? You've heard several different mechanisms. They all coexist. It just depends on where you are, what you're looking at. If you're up in Nepal, or if you're down by the sea, if you're up at the surface of the ground, or if you're below the ground. All these things are going on at the same time. But in the shallow sediments where the current 10 million wells are, we just find that it's probably this, not so much the dissolution of these arsenic-bearing minerals that's controlling the arsenic in the water, but it's probably the desorption of arsenic that's just on the surface of minerals that's controlling the release. There's no single way to stop this problem or to solve this problem for the people of Bangladesh. But what we have to do is find alternative sources of clean water. And the reason we can do it just that simply is that arsenic is always excreted from your body continually. So if you just stop drinking arsenic-contaminated water, your lifetime outcomes are going to improve. And if you're going to get skin cancer, you might get skin cancer, but it's not necessarily fatal. So stopping drinking contaminated water is the cure. Some other cures that have been proposed, like chelation therapy, that's when you give people a dose of another chemical that sort of goes and pulls all the arsenic out of your body. It might work for one time, but it doesn't make a lot of difference when the real problem is your lifetime dose. You heard it takes 10, 20, 30 years for this to happen. So one chelation treatment is not going to cure you. And it might give people the false impression that they can keep drinking arsenic-rich water. There also has been suggested that vitamin therapy, particularly vitamin A, which is good against skin ailments, could help. In Bangladesh, there's been a program for a good 5 years or more now of testing and labeling the wells, but there are problems with that. What they do is, with field kits, they go around, and if the well has more than 50 parts per million, or per billion rather, they paint it red, and if it's lower than that, if it's safe, they paint it green. One problem is to tell people that the contaminant is not bacteria. You know, all their lives it's been bacteria, 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 and boil your water. So if they see a red well, they might go boil the water and think they're getting rid of the arsenic. In fact, they might be concentrating the arsenic. There's a reluctance among people to share their wells, and it's partially a privacy issue. There's a lot of issues that go into it. But if you have everyone a lot of the wells are sited right in the courtyards of people's houses. Remember, this is their water supply, their private water supply. So you wouldn't want 50 people coming to your house every day to get water just because you had the clean well in the neighborhood. There's also a fear that with increased use of the well, it will become contaminated. This is in part a mis idea, but in part there's some evidence that the millions of wells that have been put into the ground are changing properties of the aquifer at depth. So people are taking out so much water that things are changing underground. And it's hard to motivate people to walk farther, especially the women who have the lion's share of the work in carrying and drawing water, to walk so far to clean water. There's been studies that show that initially when they go out and do their education programs, tell people don't drink the arsenic water, and then come back 5 years later, people are sort of, the urgency of it is forgotten. When that water is so clean and clear, it looks good to drink. And it's such a pain to carry your 5 or 6 buckets down, much further away to draw water. Also, the paint comes off the well with time. That's a simple one, but when you have 10 million of them to repaint, it's not necessarily a trivial issue. A lot of people are advocating water treatment, and right now there's a $1 million prize being offered for the safest or the quickest, the cheapest solution for the people there. But I think it's really a short-term solution because with these kind of scenarios, you have some kind of material, absorbent, or to suck up the arsenic, and then the clean water you draw out from below. But what are you going to do with that sorbent? You've created another waste, a super concentrated arsenic sludge, mud, that you've got to do something with. And that's non-trivial. Some of the traditional methods that the Bangladeshis have used, if they were a little bit improved upon, offer some hope for a long-term solution. They've long used what they call pond sand filters. And so it's just like you say, you filter the water through sand with some special bacteria on the top of it to keep it clean. You keep it clean from the bad bacteria. This is a modern version of that, where they've sort of bricked it all in so that things don't just fall in it and people don't go take a bath in it, which people used to do. And they're getting the water out from right here. You see the woman with her 4 or 5 jars that she's got to go get water several times a day probably to do her thing. So this is one option, but you really have to be careful to make sure that they don't get contaminated with the microorganisms. That was the whole reason that these wells that people stopped using these kinds of wells in the first place. Another option is the rainwater harvesting. Remember, we mentioned that there's monsoons, there's these huge volumes of water, like we can't even imagine how much water falls during the monsoon, and you can catch it. Like in this system, a concrete catchment, and there's a pipe here. The water that's running off the roof is being shunted in there. And that's also an option, but there's some capital outlay that would need to be done. And that's expensive for the people. Another idea that's being considered is to use the water that's deeper than the 150 meters. This water is in what we call the deep aquifer down here at about 300 meters. And you can't get to that with the little drill rig and the few fellows like I showed you in the picture. You need a real heavy equipment to get down there. In some places, it's not good to drink. Like shown in this diagram, here it's brackish or saline. Down here it's fresh. So the idea is to use that only for drinking and drill down into it. But obviously, that's going to require a lot of money. We've seen arsenic in pyrite in the deep aquifer. This is an example of the kind of arsenic we see there. And it's pretty small material. And that and other chemical evidence shows that it formed right there. It wasn't carried all the way from the Himalayas. It formed in place there. But anyway, back to the deep aquifers. It costs a lot to drill down there. And it's not possible, there's not good water for at least 100 kilometers in from the coast. So that's not going to be a solution for everywhere. There's the potential to contaminate the deep aquifer from the one above it if water is drawn down into it, and there's various ways that could happen. Number one, you construct the well not so good. That could happen. But also, I mentioned this aquitard and aquiclude business. There's another layer that separates the upper and the lower. Well, there's not much known about the confining properties of that lower aquifer. We don't know if there's an aquitard that goes all the way across the country and keeps the arsenic-rich water separate from the arsenic-poor water. And there's the same problems about sharing and the distance. These would all be community wells, these deep wells. And so the same issues would be a problem. So ultimately, the solution is going to require a lot of cooperation between governments, inside, the government of Bangladesh, people outside, non-governmental organizations, researchers like myself and others. There's been some resentment, some well-founded resentment of all the scientists that come in and study and leave, and nothing really happens for the people. And there's not been the best coordination between the various responses, not the most pragmatic solutions to really help the people in the short term. But ultimately, to sort of paraphrase the words of the song George Harrison wrote about the famine problem, we all have to do something, whatever we can, to help save some lives from this terrible silent tragedy. Thank you.
So, Andrea, thank you very much. Does anybody have a question for Andrea before we go? I think there's one at the back there.
Consider the possibility of feeding the people in Bangladesh selenium?
Well, yes, there is a known, it's known that if you take selenium at the same time you're taking arsenic, that it will lessen the arsenic poisoning. And it was discovered actually with X-rays from here that selenium and arsenic get together in our body and form a new material that then passes out of our body. So that is an option, but just another expense when you have to think about the poverty of the people there and how to get it to everyone and how to get the right dose, because selenium itself can also be a poison if too much is taken.
Bangladesh grows a lot of rice. Would rice contain the arsenic?
It can. One study showed that the rice grown in Bangladesh using water, irrigation water that was very high in arsenic, did not contain more arsenic than rice that was grown in Japan, far from any arsenic source. But other studies have shown that it's really the cooking water that puts the arsenic in the rice. So if you use arsenic-rich water to cook the rice, of course the rice takes up all that arsenic in the water and it's not released. So it's the cooking water that's the real problem with the rice.
Are there any other plants that take arsenic?
Yes, there are special plants called hyperaccumulators that take up arsenic to amounts much greater than even would be found in the sediment that they're in. But even things like tomatoes, lettuce, take up some amount. But in the main, it's not the arsenic in the food that's really the problem, except where you've had to cook the food in water.
It's my understanding that there's a concentration of arsenic in the Nevada plain area with increased building in Reno. Would that not be a good place to settle?
Well, there are a lot of problems with arsenic at the surface of the ground in the western United States. And there's a lot of mining activity in Nevada. And so, and it's a very arid locale, so you get a problem of dust. I had a slide in, I had to take it out. You saw how long my talk was already, but there was a slide about the different ways you can get arsenic into your body, and inhalation of arsenic-bearing dusts is definitely an issue. But also in Nevada, there's arsenic in the groundwater, a considerable amount, and as I mentioned, in the western United States, we're pretty low on water. And so, well, there you have the issue of arsenic that's associated with gold, with pyrite from the historic gold mining. So all the gold was taken out, but the arsenic was left behind. So you have the same situation. I could tell you 3 or 4 instances where people built their houses or even whole subdivisions built on mine tailings. And then they found out later that the soil beneath their feet has hundreds or thousands of parts per million arsenic. But again, it's not, the concentrations are scary, but it's more a question of the controls on the release that are the issue.
So free-flowing surface water, it's not as concentrated?
Under most conditions. There is, the city of Los Angeles receives a lot of their single largest source of arsenic comes from one site that's a geothermal source. Arsenic is coming up out of the ground and carrying a lot. And in this one creek, Hot Creek it's called because it's hot, there's a lot of arsenic in that surface water. So in special situations, especially geothermal, yes, you could have a lot of arsenic in surface water, but generally, no.
So is this accumulating in wildlife, whatever wildlife value?
Arsenic is not a bioaccumulator, so like selenium or mercury. It doesn't get stored in our fatty tissues and cause problems. We can accumulate it in the keratin, in nails and hair, but it's generally not available and not toxic in that form. So it's really, it's the readily available inorganic stuff that constantly passes through but causes damage on the way. Seems to be the point. Causes damage on the way out. And so the bioaccumulation thing is not a factor. It's this constant dose deal that's the factor.
Good. Well, once again, oh, is there one more question? Excuse me.
Your talk has come at a a very interesting one. About 2 days ago, I read a news in the XANES and Mercury Times that our own city, Palo Alto, has been affected by a lot of arsenic because of insecticide which was being sprayed. I don't know whether you read that one. And some company is willing to remove that arsenic. How is it possible? It can only be washed out by rain.
Yeah.
So I do not know what method they could adopt. I mean, because your field of work was something totally different. Perhaps you could throw some light on that. How?
I'm not familiar with that they're currently spraying with arsenic-based insecticides in this country. I knew that there was a site in East Palo Alto where they had stockpiled some arsenic-bearing materials to be used in for some chemistry.
Our county has agreed. I don't know what you call Palo Alto. The municipal there, they have agreed with some contracting firm to remove the arsenic.
Oh.
How they could do it? That's my idea.
I don't know. I'm not familiar with it. I'll have to look in the newspaper. Thanks.
Good. Well, time for just one more, and that'll be the last question.
When arsenic replaces some of the atoms in DNA, what exactly happens when the cell does mitosis?
I'm not sure. I don't know all the details of it. But it's replacing phosphate in the DNA, and phosphate forms the backbone of the DNA, right? But I can't speak to exactly how that would affect a cell during mitosis, sorry.
So, Andrea, thank you very much again.